In this video, we'll talk about linear independence. Remember, we have linear independence amongst a set of vectors if the only way that we can make the zero vector using a combination, a linear combination of all the vectors in the set that we have, that we're talking about, right up to vector xn, if the only possible way that we can get that zero vector is if every single one of these c constants or c scalars is zero. If there is any way that we could make any of these c scalars non-zero, then we say we have linear dependence. Okay, so if all of the c's, if c1 equals c2 equals c3, right up to cn, if they all equal 0, and that's the only solution, that means we have linear independence. Linear independence would also mean that we cannot make one of these vectors x1, x2, right up to xn with a linear combination of the other vectors in the set. So that's what we're talking about when we're looking at linear independence. An example of that is if we have the vectors a is equal to 3, 4, and b equals 12, 16. Straight away, by looking at these vectors, we could say, well, b is just 4 times our vector a. And from that, we already know that they are linearly dependent. So we could start out with something like that. We can clearly see that there's a scalar multiple, so we're done. It gets a little bit trickier if we have more vectors, for example, or if perhaps we've got higher dimensions in our vectors. So let's see the other way we can do this. We'll still work with the vectors a and b, but what we will try to do is we will try to make the zero vector using c1a plus c2b. What we want to do is we want to see, is there any way we can get this zero vector other than by making both c1 and c2 0. So the zero vector in this case would be a 2 by 1 vector because a and b are both 2 by 1 vectors. So we're trying to find 0, 0 is equal to c1 outside of 3, 4 plus c2 outside of 12, 16. What we'll do is we'll look at these element by element. Here we're looking at 0, 0 is equal to 3c1 plus 12c2 and 4c1 plus 16c2. We'll keep going now. Let's look at this first element, element 1. From element 1, or cell 1, we know that 0 must be equal to 3c1 plus 12c2. Let's rearrange this. We'll take 12 across to the other side. We've got negative 12c2 equals 3c1. We'll divide both sides by 3. Minus 12 on 3c2 equals c1. Minus 4c2 equals c1. Okay, let's keep going and let's work out what happens for cell 2. I'll just underline this here. This is the equation that we need to satisfy in order to get that first 0 in red there. Now let's look at cell 2, and we're going to be looking at this equation over here. We need to satisfy that. So, for cell 2, we need to make sure that 0 equals 4c1 plus 16c2. We'll rearrange. We'll take the 16 across to the other side. We've got negative 16c2 equals 4c1. We'll divide both sides by 4. We've got minus 4c2 equals c1. And this is the equation that we need to satisfy for cell 2. Let's just have a look back up here. We can see that these equations are exactly the same. So here, essentially, because these equations that we have to satisfy are exactly the same, it means we only have one equation but two unknowns. And when we have one equation, two unknowns, that means we should have infinitely many solutions. Infinitely many solutions means that, well, we definitely have a non-trivial solution, and trivial solution was just for our C1 and C2 to be 0, but we definitely have at least one non-trivial solution that works out, we get the 0 vector. An example solution to this one would be if we just set C1 to be anything we like. So let's keep going. Oops. Okay. Here we have, we'll let C1, or let's let C2 equal 6. If we let C2 equal 6, we know that C1 equals minus 4C2, just from the equations we found above. That means that here, C1 equals minus 4 times 6, which equals negative 24. So let's use those and see if we do, in fact, get that 0 vector. So here our C1 is negative 24, C2 is 6. So what we're looking at is negative 24 times our A vector, which was 3, 4, plus 6 times our B vector, which was 12, 16. Okay, negative 24 times 3, we get negative 72, plus 6 times 12 is 72. Negative 24 times 4, we get negative 96, plus 6 times 16, we get 96. And when we add those up, we get 0, 0. Now, because there is a way that we can get non-trivial solutions to the linear combination adding to 0, we can say the vectors A and B are linearly dependent. I'll do another video where I talk about an example that we end up with linearly independent vectors, but that's it for now.